Alright, we're going to work through a few examples of simplifying some square roots. So the first one we're going to look at is simplifying the square root of 125. So we're going to look for the largest perfect square that goes into 125, which happens to be 25. 125 is going to be 25 times 5. So 5 quarters is $1.25, and let's go ahead and rewrite this here. And we're going to use a property of square roots is if we have square root of a, b, it's going to be equal to the square root of a times the square root of b. Of course, the radicand is understood to be positive in this case. So what we'll do is we'll rewrite this as the square root of 25 times the square root of 5. And that'll become 5 square roots of 5. Okay. The next one we'll look at is the square root of 72. And 72 is 36 times 2, so that's the largest perfect square. And we can rewrite that as square root of 36 times the square root of 2. The square root of 36 is 6, so we get 6 square roots of 2. The other way you can do these is you can break 125 down into 5 and 25, 5 and 5, and 125 is 5 times 5 times 5. So if we were to take the square root of that, there's our 25, square root of 25 is 5, and 5 is left over. If we do 72, 72's got a lot more stuff going on, so 72 would be 2 and 36, 2 and 18, 2 and 9, and 3 and 3. So 72 would be 2 times 2 times 2 times 3 times 3. And if we take the square root of that, 2 times 2 is 4, square root of 4 is 2. 3 times 3 is 9, square root of 9 is 3, and we'd have a 2 left over. 2 times 3 is 6, 6 root 2. And that's certainly another way you can do that. Okay, let's work through a few more examples. So let's say we're going to assume the variables are positive, and I'll do another video where the variables are not assured to be positive. I'll show you an example of that in a minute. So here we're going to assume all variables are positive, so we don't have to worry about taking square roots of things like x squared. So if x is positive, then the square and the square root are just going to cancel each other out, and we're just left with x. Or if we want to take the fourth root of x to the 5th times y to the 8th times z to the 3rd, and in order to get out of a fourth root, you need to have a fourth power, or you need to be 4 of a kind. That means 4 of a kind would be x times x times x times x, 4 of them. So what we're going to do is we're going to rewrite this. This is going to be the fourth root, and then it's going to be x to the 4th times x, and that gives us the x to the 5th. Y to the 4th times y to the 4th. Remember, when you multiply like bases, you add the exponents, so that's y to the 8th. And then z to the 3rd. We'll put the fourth root outside. So we're able to take out an x. The fourth root of x, the 4th is x. And we'll be able to take out 2 y's. So we'll have 2 y's to make a y squared. And then, unfortunately, the poor x and the z to the 3rd, they don't have enough to get out of the fourth root, and that's all we can do. That's as far as we go. All right, let's do a few more examples of those. Say we want to do the cube root of 120, x to the 5th, y to the 9th, z to the 12th. And I'm going to show you a little trick to be a little bit more efficient here. So we go through the list and perfect cubes, and we find that 8 times 15 is 120. And then we need third powers to get out of the third root. So we can rewrite x to the fifth as x cubed times x squared. And then we're going to use the power rule for exponents, which is if you have a to the m to the n, you multiply your exponents. And what I want is I want things to the third power so that the third power will cancel with the third root, so we'll get stuff out. So what we're going to do with the y is we're going to write it as y to the third cubed, and if we multiply those threes together we'll get 9. And then the z, we can write that as z to the fourth and then cubed. So what that does is that allows us to not have to do this y cubed, y cubed, y cubed. There's our y to the ninth. Z cubed, z cubed, z cubed, z cubed. There's our z to the 12th. And we don't want to do as much writing there. So then we'll go ahead and bring out the stuff that the cube root will interact with correctly. It'll cancel out. So the cube root of 8 is 2. The cube root of x cubed is x. The cube root of y cubed cubed, so one of the cubes is going to cancel out, and we'll have y cubed coming out. And then z to the fourth cubed, the cube root will cancel the cube, and we'll be left with z to the fourth. So unfortunately, poor 15 and the x squared, they got to stay in the square root. Not the square root, the cube root. Okay, let's do one or two more examples. Say we want to do the cube root of x plus, I think I did 17. 17 to the third power. The cube and the cube root will undo each other, and we'll just be left with x plus 17. And something a little bit more exciting. What if we want to do the fourth root of x plus 17 to the I think that's an eighth power. Yeah, it's an eighth power. So we're going to rewrite that as x plus 17 squared, and then to the fourth power, so that I'll have a fourth power that'll interact with a fourth root. And they'll cancel us out, and we'll be left with x plus 17 quantity squared. Okay, maybe we'll do one more just for fun. What if we wanted to do the cube root of x plus 17 to the fourth, and we'd have to rewrite that with somebody with a perfect cube, so x plus 17 cubed, and then x plus 17. So what's going to happen here is the cube and the cube root will undo each other, so an x plus 17 gets to come out, and then we have a poor x plus 17 that's got to stay inside the radical there. Okay, it'll just take some practice and you'll get the hang of it.